Hello, students. We are going to talk about waves today, and this is section 7 through 14 of chapter 11 in your textbook. So, wave motion is mechanical motion, or at least in a mechanical medium, wave motion is mechanical motion. So, the motion of the pulse or the peak or the trough of the wave still follows our definition for speed and velocity and acceleration as for particles, but a wave is a continuous oscillation of um, some physical medium, be it water, as in the pictures here in the slide, or a rope, a slinky, or air molecules, as in the case of a sound wave. So the individual particles of this extended medium oscillate in place, which is why we started with oscillations. They oscillate up and down in the case of the rope that you're seeing at the bottom of the slide, or they oscillate forward, backward, as in a compression wave, like a sound wave. The particles oscillate about some fixed location as that wave shape, as the crest moves from left to right across the screen, as in the case of the rope, or out in that circular pattern, as in the case of a wave on the surface of the water. So all types of traveling waves transport energy, whether it's a mechanical wave or an electromagnetic wave. What's moving from place 1 to 2, so in this picture from the hand to the other side of the rope, is energy. The particles in the medium, as we just said, oscillate in place. They go up and down or side to side in some sort of repetitive oscillatory motion. They aren't moving from place 1 to place 2 across the medium. It's only that wave shape that moves from one place to the other, and the wave shape is transmitting energy. All waves have a source, and all sources of waves are vibrations. A continuous wave needs a vibration that's continuous, and if that source vibration is simple harmonic motion, then the actual shape of the wave will be sinusoidal. So characteristics of waves are very similar to the characteristics of oscillations because the source of all mechanical waves is vibration. So a wave will have an amplitude, a frequency, and a period, same as for oscillatory motion. The definitions are the same as well. The amplitude of the wave is the peak or trough, the maximum displacement, either positive or negative, from equilibrium. For wave, that means the position of the medium when no wave is passing through. The frequency is the number of waves that pass a particular point in time. You can also translate that to the frequency of the source, so the number of oscillations of a particle in the medium per time. And then the period is the time it takes for one complete wave to pass, or the time it takes for the mother oscillation to complete one oscillation, or the time it takes for one particle in the medium to oscillate one complete cycle. That got a little mixed up as I said it, but I hope that makes sense. So then we can talk about the way a wave spreads out over space in a medium. This is the new thing. So a wave is not a single particle oscillating in a single place. It's particles connected together, oscillating sort of in tune with each other as the wave shape passes through the medium. So we have an oscillation of every particle in place in time, and then we have the medium as a whole in space at any time, any moment in time. And so that sort of moment in time snapshot of the wave motion shows you the size of the wave, and that's measured amplitude, of course, the height, right, the crest or trough, but also the side to side motion, so peak to peak or trough to trough, the length of the wave. So wavelength is usually measured peak to peak or trough to trough, just because those are the easiest points on a wave to pick out, but it can be any successive identical parts on the wave. Okay, So then we have velocity. As I said, the wave crest or trough or any part of that wave shape moves through space, just like we've defined velocity previously. Since the distance a wave travels can be marked out as one wavelength or multiple wavelengths, and the time it takes for one complete wave to pass a particular point in space is measured as period, we can identify the velocity of the wave as we have before, the change in position of, let's say, a crest per time, same definition for wave or for velocity that we've always had, but we can also now translate it as distance traveled is one wavelength, and by definition, the time it takes for one wavelength to travel through space is the period. So this is the wavelength, and this is the period. And then we can rearrange that any way we like. This is one of the equations on your AP equations table. There's really not a lot happening on the AP equations table for waves. It's very much conceptual after this. So here's an example question. A boat is moored in a fixed location and waves make it move up and down. If the spacing between the crests is 20 meters and the speed of the waves is 5 meters per second, how long does it take the boat to go from the top of a crest to the bottom of the trough? I hope you answered 2 seconds. So the period of the wave, according to wave speed equation, should be 4 seconds. But the question is asking you half of the period, crest to trough, not crest to the next crest. So you answer half the period of 2 seconds. All right, so microwaves. This is not a mechanical wave, but electromagnetic waves do have some of the features of mechanical waves, namely that they follow the same wave speed equation and that you have a frequency of oscillation of an electron that causes the wave equal to the frequency of the electromagnetic wave itself. So microwaves travel at the speed of light, which is 3 times 10 to the 8th meters per second, at a frequency of 10 gigahertz. So the capital G, gigahertz, means 10 to the 9th. These waves cause the water molecules in your burrito to vibrate in your microwave machine. What was their wavelength? So I hope you answered 3 centimeters. You do have a little bit of units conversion to manage here, but using the wave speed equation, translating from period to frequency, however you managed that, should lead you to 0.03 meters or 3 centimeters. All right, so there are 2 major classifications for mechanical waves. They are transverse and longitudinal. Those are your 2 options. And they have to do with the oscillation of the medium compared to the motion of the wave form itself. I can't remember if I have a separate slide. Yes, okay. So in a transverse wave, the medium oscillates perpendicular to the direction of the motion of the wave form. So the top picture, I can't point to it. The top picture in your slide is a transverse wave. And a transverse wave typically has a snapshot that looks something like a sine wave. You see a snapshot in time that looks like a sine function or a cosine function. So again, it has to do with the medium. Those are the particles oscillate perpendicular to the wave velocity itself. So in the slinky picture, one crest of the wave is going across your screen to the right. And as that crest goes to the right or to the left, a particle on that slinky oscillates up and down, vertically up and down in the picture. Transverse. The other option is longitudinal. And in a longitudinal wave, the particles of the medium oscillate parallel to the wave's velocity. So a crest, which in this case is a compression. So I have a part of the slinky that's compressed. That compression travels along the slinky in successive compressions to the right And the slinky itself, so a little particle on the slinky oscillates left, right, left, right, left, right, left, right. So this is a compression wave.